NASA spent $1.2 billion building the engine of the future, and then killed it. The X-33 program is officially cancelled. Inside a warehouse at Stennis Space Center sits a fully functional engine called the XRS-2200. It's been test-fired extensively. It works. It's the world's first flight-ready linear aerospike, an engine design that could theoretically make rockets 30% more efficient at every single altitude, from sea level all the way to vacuum. And with that cancellation, it gets locked away. Nobody flies it. Nobody builds another one for almost 20 years. The Aerospike engine becomes a thing nobody in the rocket industry wants to talk about. But here's the thing. Fast forward to 2024, a small company in Barcelona, Spain, fires a 3D printed Aerospike engine. Another company in Romania is building an Aerospike powered rocket called the Eco Rocket. An American startup called Stoke Space is flying an Aerospike-derived second stage that survives re-entry without a heat shield, and in December of 2024, an AI designed a copper Aerospike engine, and it hot-fired in a matter of weeks. The Aerospike was never a bad idea. It was an idea that arrived 30 years too early, and now 4 things have changed simultaneously that make the Aerospike not just viable, but potentially inevitable. 3D printing, AI-driven design, new materials that didn't exist in 2001, and computing power that lets you simulate 1,000 spike geometries before you cut a single piece of metal. This isn't a story about an engine that failed, it's a story about an engine that arrived before the world was ready for it, and why it's coming back. Every rocket you have ever seen fly, Saturn V, Falcon 9, Space Shuttle, Starship, has a fundamental design flaw built into it, and it's not a small one. A rocket nozzle is shaped like a bell for a reason. The exhaust gases exit the combustion chamber at insane temperatures and pressures, and the bell shape expands those gases, converting thermal energy into kinetic energy. That's what produces thrust. The wider the bell, the more expansion you get, and the more efficient the engine becomes. But there's a catch. The shape of the bell is fixed. It's a single piece of metal and is optimized for exactly one altitude. At sea level, the atmosphere is pressing in on the exhaust plume with 14.7 pounds per square inch of pressure. So a sea level optimized nozzle is relatively narrow. It prevents the exhaust from overexpanding and separating from the nozzle wall, which would create violent instabilities that can destroy the engine. The F1 engines on the Saturn V, for example, had a specific bell-shaped design for a maximum thrust at launch, and they were incredible at sea level. But the moment the rocket started climbing, that same nozzle became less and less efficient with every meter of altitude it gained. Now here's the other side of this problem. Upper stage engines and vacuum engines, think the RL-10, the Merlin vacuum on Falcon 9 second stage, these have massive nozzle extensions, huge bells, because in the vacuum of space, there's no atmospheric pressure fighting the exhaust. So the plume can expand as much as possible. The wider the bell, the better the efficiency. But you cannot fire a vacuum-optimized nozzle at sea level. The exhaust would overexpand, separate from the walls, and the resulting flow instability would tear the nozzle apart. This is not a theoretical problem. This has destroyed engines in testing. So here's the dilemma every rocket designer faces. You have to pick, do you optimize the nozzle for sea level and sacrifice efficiency at altitude, or do you optimize for vacuum and accept that the engine can't fire until you're already in space? There is no nozzle shape that works well at both. Every rocket flying today, every single one, is a compromise between these two extremes. And that compromise costs efficiency. At sea level, the engine is fighting the atmosphere. At altitude, the nozzle is too narrow to expand the exhaust fully. You're leaving performance on the table at every point in the flight. Which raises a question, what if a nozzle could change its shape based on altitude? Automatically, with no moving parts. That's exactly what the Aerospike does. Let me elaborate. Instead of a bell containing the exhaust inside a closed nozzle, the Aerospike inverts the entire design. You take the spike, a central ramp or cone, and you fire the exhaust gases around the outside of it. There is no outer wall. The atmosphere itself acts as the outer nozzle wall. Here's what that means in practice. At sea level, the ambient air pressure is high. That pressure squeezes the exhaust plume inward against the spike. The plume stays tight, contained, and controlled. Exactly what you want at low altitude where overexpansion is the enemy. Then, as the rocket climbs and the atmospheric pressure drops, the plume naturally expands outward. The invisible outer boundary, the point where the exhaust meets the atmosphere, moves wider. The effective expansion ratio increases automatically. By the time the rocket reaches vacuum, the plume has expanded as far as physics allows, delivering maximum efficiency, exactly what you want in space. No moving parts, no gimbal, no variable geometry, no switching between sea level and vacuum nozzles. The atmosphere does all the adjusting for you. The engine is self-compensating across the entire flight envelope. Now there are two main configurations. The linear Aerospike, think of a ramp or wedge shape with exhaust flowing down both sides in a rectangular pattern. That's what the XRS 2200 was. Two parallel rows of thrust cells firing against a central ramp. The other configuration is the toroidal or annular Aerospike. Picture a cone or a plug, with exhaust flowing around it in a ring. That's what most modern Aerospike developers are pursuing, because it's easier to cool and easier to 3D print. Think of it like this. A bell nozzle is like a fixed width pipe. It's perfect for one flow rate. Change the pressure, change the altitude, and that same pipe is either too wide or too narrow. It leaks efficiency everywhere except at its design point. An Aerospike is like an infinitely adjustable nozzle, except there's nothing to adjust. The atmosphere does the work. The spike just sits there, and physics handles the rest. And the numbers are not subtle. A conventional bell nozzle loses roughly 10 to 15% efficiency across the full flight profile compared to what's theoretically possible at each altitude. An altitude compensating Aerospike, in theory, loses near zero. You get sea level thrust when you're at sea level, and vacuum thrust when you're in vacuum. The same engine, the same nozzle, the entire way up. That efficiency gap, 10 to 15%, may not sound dramatic, but in rocket engineering, where every kilogram of payload is fought over, where fuel mass fractions dominate the equation, 10 to 15% is the difference between needing a second stage and not needing one. It's the difference between throwing away your booster and reusing the entire vehicle. It is quite literally the difference between a rocket that stages and a rocket that doesn't. The Aerospike almost flew in 2001, and the program that was supposed to make it happen was one of the most ambitious things NASA has ever attempted. Venture Star, a single stage to orbit spaceplane, no staging, no dropping boosters, no throwing away hardware. Take off vertically, fly all the way to orbit, deliver your payload, then glide back to runway like the space shuttle. Refuel it, fly it again, the holy grail of spaceflight. A fully reusable vehicle that goes from runway to orbit and back without leaving any hardware behind. The engine that was going to power this, two XRS 2200 linear Aerospikes built by Rocketdyne. These engines were extensively test-fired at Stennis Space Center, and they worked. This is the part of the story that gets buried. The Aerospike engine was not the failure point of the X-33 program. The engines performed. They produced the thrust they were supposed to produce. They demonstrated altitude compensation in ground testing. The engine side of the program was a success. What killed Venture Star was the fuel tank. Specifically, the composite liquid hydrogen tank. NASA and the Lockheed Martin attempted to build a multi-lobed carbon fiber composite tank to hold liquid hydrogen at cryogenic temperatures. This was completely novel. Nobody had ever built a tank like this before, and during pressure testing, the tank failed. Catastrophically, it delaminated. The composite layers separated. In one test, the tank literally came apart under the pressure it was supposed to withstand. NASA pulled funding in March of 2001. Total program cost, roughly $922 million from NASA, over $1.2 billion total including Lockheed Martin's investment. And with that cancellation, the single stage to orbit dream died. Venture Star was shelved, the XRS 2200 engines were mothballed, and the entire concept of the Aerospike engine became toxic. Here's the problem. The Aerospike didn't fail, the fuel tank failed. But in minds of NASA leadership, in the minds of investors, in the minds of the aerospace industry writ large, the Aerospike became the engine that killed X-33. It got blamed by association. Nobody wanted to touch Aerospike research for nearly 2 decades. Venture capital would see the word Aerospike in a pitch deck and run. NASA had what you could only describe as institutional PTSD. The entire propulsion concept was frozen out. But the engine was fine, the test data was good, the physics was sound, and buried underneath the program failure was the most frustrating kind of truth. The kind where the right idea gets blamed for the wrong problem. There was, however, one genuine technical issue with the XRS 2200 that would have been a problem even if the tank hadn't failed. And it's the same issue that haunts every Aerospike design: cooling. In a bell nozzle, the hot exhaust contacts one surface, the inner wall of the bell. You can run coolant through that wall, regenerative cooling, just like every modern rocket engine does. This amount of surface area you need to cool is manageable, but in an Aerospike, the central spike is surrounded by exhaust on all sides. It's bathed in flame from every direction. The surface area that needs active cooling is dramatically larger, roughly double depending on the design. And in the 1990s, with the copper alloys and manufacturing techniques available at the time, this was a problem that didn't have a clean solution. You could cool the spike, but the cooling system added weight, and that weight ate into the efficiency advantage that made the Aerospike attractive in the first place. The XRS 2200 engineers made it work at subscale, but scaling it to a full orbital class engine with 1990s materials, that was going to be brutal. Now, this brings me to the next point. 4 things have changed since 2001 that fundamentally alter the Aerospike equation, and none of them existed when the XRS 2200 was sitting on that test stand. Factor 1, 3D printing, also called additive manufacturing, and this is the big one, because it directly solves the cooling problem that was the Aerospike's Achilles heel. In the 1990s, if you wanted cooling channels inside a complex curved surface like an Aerospike, you had to machine them. You'd fabricate the spike in sections, cut grooves into each section, braze or weld the sections together, and hope the cooling channels lined up. This was incredibly expensive, incredibly slow, and the resulting part was heavy. Every joint was a potential failure point. The complexity of the internal geometry was severely limited by what you could physically machine. With modern 3D printing, specifically laser powder bed fusion for copper alloys, you can print the entire spike as a single piece. Cooling channels running through it in whatever geometry the thermal analysis says is optimal. Curved channels, branching channels, channels that change diameter along their length, geometries that are literally impossible to machine. And you print them in one operation. No joints, no brazing, no assembly. The spike comes out of the printer with all of its internal cooling already built. Factor 2, AI-driven computational engineering. And here's where the story connects directly to something we covered in a previous video. In December of 2024, Leap 71, the same company whose AI designed a working rocket thruster from scratch, used their Neuron computational model to design a copper alloy Aerospike engine, and they hot-fired it. Neuron doesn't use CAD software, it calculates geometries from first principles, physics equations, thermal loads, fluid dynamics. It doesn't guess, it computes. An engineer in the 1990s would spend weeks laying out cooling channels by hand, running a simulation, tweaking the design, running another simulation, 3 or 4 iterations if they were lucky. Neuron can compute thousands of channel geometries overnight. converge on the optimal one, and output a file ready for 3D printing. The cooling problem that was the Aerospike's fatal flaw, an AI can solve while you're sleeping. Factor 3. New materials. NASA developed a family of copper alloys called GrCop42, GrCop84, copper chromium niobium compositions with dramatically higher thermal conductivity and higher strength at temperature than the copper alloys available in the 1990s. These alloys were developed for combustion chamber liners on engines like the RS-25, but they are perfectly suited for Aerospike spikes. More heat transfer with less material, thinner walls, less cooling mass. The spike can survive temperatures that would have melted the XRS-2200's copper. Factor 4. Computing power. In 1999, running a full computational fluid dynamics simulation of an Aerospike exhaust plume took literal weeks on the best supercomputers available. In 2025, the same simulation runs in hours on cloud computing clusters. You can simulate 100 spike geometries before you print one. You can run the entire flight profile, sea level to vacuum, every altitude, every throttle setting, before the first piece of metal exists. So here's what happened. The 4 things that killed the Aerospike: impossible cooling geometry, materials that couldn't handle the heat, design iteration that was too slow to converge, and manufacturing that couldn't build what the analysis said was needed. All 4 were solved in parallel, not by one breakthrough, by 4 simultaneous shifts that nobody in 2001 could have predicted. The XRS-2200 was the right engine at the wrong time. The tools to build it properly didn't exist yet. Now they do. This takes me to the next idea. If the Aerospike is making a comeback, who's actually building one? And the answer is surprising, because it's not SpaceX, it's not Blue Origin, it's a handful of smaller companies and agencies that have quietly been solving the problems NASA gave up on. Let's start with the Pangea Aerospace. Barcelona, Spain. They've built an engine called the Arcus, a methylox aerospike, biomethane and liquid oxygen, designed for a small launch vehicle called the MESO. The Arcus is 3D printed using a copper alloy. It's been hot-fired multiple times, and it's backed by the European Space Agency. Pangea claims the engine is reusable up to 10 times without refurbishment. And they didn't spend $1 billion to get there, because every tool they needed, 3D printing, CFD simulation, modern materials, already existed when they started. They just had to apply them. So a company in Barcelona did what NASA couldn't. Not because they're smarter, because the tools that didn't exist in 2001 exist now. Next, Arca Space, Romania. Now Arca is polarizing. They make some very unconventional engineering decisions, and the aerospace community doesn't always take them seriously. But here's the thing, they're building hardware. Their eco-rocket concept uses a steam-powered first stage. Yes, you heard me correctly, steam-powered. With a linear Aerospike nozzle. They fired Aerospike engines when most companies won't touch the concept. They're the wild card, but in a field where almost nobody is attempting to fly Aerospikes at all, Arca is actually attempting it. Then there's Stoke Space, and this one is different because Stoke isn't building a pure Aerospike. They're applying Aerospike principles in a way that's arguably smarter than anyone. Their second stage uses a ring of 30 thrusters arranged around a central metallic heat shield. The exhaust doesn't flow through a conventional bell. It expands against the vehicle's own heat shield. The physics is Aerospike physics. The exhaust plume is shaped by the ambient pressure, just like an Aerospike, but Stoke gets the altitude compensation for free, because the heat shield they needed for re-entry also functions as the nozzle's outer boundary. They're not calling it an Aerospike, but when you look at the fluid dynamics, when you look at how the exhaust interacts with the vehicle structure, that's exactly what it is, a distributed Aerospike that doesn't look like one. And their vehicle is designed to be 100% reusable. Both stages, the second stage re-enters and lands without a separate heat shield, because the engine is the heat shield. That's an Aerospike advantage that nobody was even talking about in the X-33 era. Now, the European Space Agency, they're not betting on one company, they're betting on the concept itself. And the institutional backing matters because it signals to the rest of the world, to the rest of the industry, that the Aerospike isn't a dead end anymore. And there are hints, patents that reference Aerospike-like nozzle geometries. Peter Beck hasn't announced an Aerospike program, but Rocket Lab watches everything. The big players, SpaceX, Blue Origin, ULA, are not pursuing Aerospikes publicly. They have flying engines, Merlin, Raptor, BE-4. You don't scrap a working engine program for an unproven concept. But every single one of them has engineers who run the numbers. Every one of them knows that if someone cracks the Aerospike at orbital scale, the efficiency advantage rewrites the competitive landscape. Here's the thing, every major space player has at least one Aerospike project. Some public, some quiet, some disguised as something else. Nobody wants to be the one still flying bell nozzles when an altitude compensating engine hits the pad. Here's the math, and it compounds in a way that changes everything. Rockets stage because of the rocket equation. Tsiolkovsky's rocket equation tells you that the velocity a rocket can achieve depends on two things: the exhaust velocity of the engine and the mass ratio. How much of your vehicle is propellant versus how much is structure, engines, and payload. The heavier your dry mass, the less velocity you can achieve for a given amount of fuel. This is the fundamental tyranny of rocketry. So what do rocket designers do? They stage. They throw away the empty tanks, the heavy first stage engines, the structures that's no longer needed, and the upper stage continues with a fraction of the original mass. Staging is a brute force solution to the rocket equation. It works, but it's expensive. Every stage you throw away is hardware that costs millions to build. Now, an Aerospike changes this equation in two ways. First, the altitude compensation means the engine operates near peak efficiency at every altitude. That's worth roughly 10 to 15% more specific impulse across the full flight profile compared to a fixed bell nozzle that's optimized for a single altitude. Second, and this is the thing that people miss, the Aerospike's shape integrates with the vehicle structure in ways a bell nozzle can't. Stokes Space's approach proves this. The engine and the heat shield become the same structure. You eliminate the mass penalty of carrying a separate thermal protection system. Combine these two effects, the efficiency gain and the structural integration, and the dry mass fraction of the vehicle improves enough that the rocket equation starts to tilt. Single stage to orbit, which was mathematically impossible with 1990s technology, begins to look viable. Not easy, not cheap, but physically possible. And here's where it compounds. If an SSTO Aerospike vehicle could deliver payload to orbit for, say, $500 per kilogram instead of Falcon 9's roughly $2,700 per kilogram, the entire launch market resets. Satellite constellations get cheaper to deploy. Space stations get cheaper to build. Lunar logistics, delivering cargo to the moon, gets cheaper at every link in the chain, because every kilogram you save on launch is a kilogram you don't have to pay for. The landing advantage is equally significant. A conventional rocket that wants to land propulsively, like Falcon 9, needs engines that can throttle deep and fire at sea level. An Aerospike doesn't need a separate landing engine. The same spike that was efficient at altitude in vacuum is also efficient at sea level during descent. It works in both directions. No separate landing burns with different engines. No complex staging sequences. One engine, one vehicle, launch to landing. What does this mean exactly? It means the Aerospike doesn't just prove existing rocket architectures, it makes entirely new architectures possible, architectures that the math of bell nozzles ruled out. But there's a problem, actually quite a few. Problem 1, cooling at orbital scale. A 5,000 Newton Aerospike, like the ones Pangea and Leap 71 are testing, is manageable. This spike is small, the surface area that needs active cooling is proportional to the thrust. But when you scale it up to a full orbital engine, 500,000 newtons or more, the spike surface area grows dramatically. More surface area means more heat to manage. More heat means more coolant flow. More coolant flow means heavier pumps, larger plumbing, more mass. And every extra kilogram of cooling hardware eats directly into the efficiency advantage that made the Aerospike attractive in the first place. This is not a physics problem that's unsolvable. It's an engineering optimization problem. The question is whether the cooling system mass penalty at orbital scale is small enough that the altitude compensation advantage still nets positive. Nobody has proven this at scale. Nobody. Problem 2. Thrust vectoring. A bell nozzle engine steers the rocket by gimbaling, tilting the entire engine assembly on the hydraulic or electric actuators. This is a mature, well understood technology. Every orbital rocket uses it. But an Aerospike does not gimbal easily. The spike is integrated into the vehicle structure. Tilting it would tilt the entire aft end of the rocket. So how do you steer with an Aerospike? Differential throttling. You divide the thrust cells around the spike into quadrants, and you throttle one side up while throttling the other side down. This produces asymmetric thrust, which creates a turning moment. It works. It's been demonstrated at a small scale. The XRS 2200 did it in ground testing, but at full orbital scale, with the response times required for active flight control, never demonstrated, never flown. And if the differential throttling response isn't fast enough, the vehicle becomes uncontrollable. That's a flight termination event. Problem 3. The X-33 Ghost. Every investor who's seen the word Aerospike in a pitch deck has also seen the Wikipedia article about the billion-dollar program that failed. The stigma is real, and it creates a classic catch-22. You can't get flight heritage without flying. You can't fly without funding. And you can't get funding because you don't have flight heritage. It's the same trap that killed every alternative propulsion concept. Rotating detonation engines, nuclear thermal, you name it. The established players have flight heritage and don't need to take the risk. The new players need flight heritage but can't afford to build it. Problem 4. Incumbent inertia. SpaceX has Raptor. It's flying. It's the most advanced full flow stage combustion engine ever built, and I've made a video about it. Blue Origin has BE4. Rocket Lab has Rutherford. None of these companies are going to throw away a decade of engine development to switch to Aerospikes. The transition, if it happens, will come from a new entrant who designs their entire vehicle around the Aerospike from day one, like Stoke Space is doing. That's a long game, and the established players will keep iterating on bell nozzles in the meantime, getting better and cheaper every year, raising the bar that an Aerospike has to clear. Here's the honest truth. The Aerospike won't replace the bell nozzle. It will coexist. Anyone who tells you Aerospikes are going to make bell nozzles obsolete is selling you something. The bell nozzle has decades of optimization behind it, and it keeps getting better. The Aerospike has to catch up from a standing start. The question isn't whether someone will try again, it's who gets there first. The Aerospike was the engine NASA gave up on, not because it didn't work, but because it arrived 30 years too early. The XRS 2200 was the right engine at the wrong time, and now the world has finally caught up. So what do you think? Is the Aerospike the future of rocketry, or is it another propulsion concept that looks beautiful on paper but will never leave the test stand? Drop your take in the comments. I'm genuinely curious where people land on this, because the space community is split right down the middle on Aerospikes, and the arguments on both sides are stronger than most people realize. Thanks for watching. I hope you enjoyed the video, and if you did, consider subscribing.